Welcome back to the deep dive. Our mission today is pretty laser-focused. We're taking a scalpel to one of the most celebrated recent paradigms in LLM post-training DeepSeek, R10.
Right. We're moving past the headlines.
Exactly. We want to critically examine the raw mechanics, the base models, the RL algorithms, just to really understand what's driving this supposed emergence of, advanced reasoning.
And it's a deep dive the community really needs. I mean, R10 felt like a revolution. It suggested you could apply reinforcement learning directly to a base model without that expensive supervised fine-tuning step.
Right, the SFT step.
And all the excitement was centered on this RL scaling phenomenon. The idea that reasoning quality just got better and better the longer the model's chain of thought response was.
A correlation that everyone just assumed was, well, beneficial.
Hmm.
But the sources we're looking at today suggest a much more complicated story. We're analyzing two core ingredients, how much of the gain is already there in the pre-training, and whether the RL itself is introducing some unintended biases.
Precisely. And the central insight, which is almost alarming, is that the group relative policy optimization algorithm GRPO, it's the backbone of this whole thing. And it contains these clear, quantifiable optimization biases. It's flawed.
In the fix.
The proposed solution is Dr. GRPO.
Which stands for GRPO done right.
Exactly. It's an unbiased method designed to keep the performance but radically improve token efficiency.
And the proof is in the pudding here. By switching to this minimalist, unbiased recipe with Dr. GRPO, the authors tuned a 7B model and achieved a new state-of-the-art.
A stunning result, 43.3% accuracy on AMI 2024.
Which just goes to show that rigor in your RL objective can be as impactful as just scaling up model size or data.
It completely shifts the focus from just scaling RL to optimizing RL. It shows that the performance ceiling isn't always about compute, but sometimes it's about these subtle biases in the loss function itself.
Okay, so let's start at the very beginning with the base models. We need to understand how these models inherently function as a question-answering policy, before RL even touches their weights.
Well, the crucial thing to recognize is the conflict. Base models are trained for sentence completion, just predicting the next token. But for R10, we need them to do structured question answering.
And that's where templates come in.
Exactly. Templates like the R1 or Quen Math template are there to structure the input and sort of coax out a chain of thought and a final answer. And for the DeepSeek and Llama models, the study confirmed, yeah, the R1 template definitely helped.
So that's standard practice. But then we get to the Quen 2.5 models.
Yeah.
And this is where, like you said, the foundation starts to crack.
It really does. The finding was that these Quen 2.5 base models hit their absolute peak answering rate 100% on the initial test when you used no template at all.
Wait, no template?
None. And it gets even weirder. Just by dropping the template, their average zero-shot performance on 5 standard math benchmarks shot up by about 60% compared to traditional few-shot prompting.
A 60% jump just from letting the model speak naturally. I mean, that is highly suggestive. What's the interpretation there?
It points straight to a powerful pre-training bias. The hypothesis is that Quen 2.5 might have been pre-trained on tons of data, where questions and answers were just, concatenated together.
It's already learned the format.
It's already behaving like an SFT model, which means if you're a researcher trying to replicate R10 with a Quen model, you're not starting from a pure baseline. You have to be really conservative about claiming these pure RL gains.
That completely reframes the starting line for RL. And this idea of baked-in behavior, it also extends to that famous aha moment phenomenon, the model self-reflecting. That was supposed to be this emergent skill from RL.
But the counterintuitive finding is that it isn't new. Nearly all the base models they looked at, including the massive DeepSeek v3 base, the 685 billion parameter model for the real R10, already had these keywords.
Before any RL.
Before the first update, the logs show it generating terms like, aha, wait, let me check.
So the behavior is latent. RL just turns up the volume on it. But does that amplification actually lead to better answers?
And that is the key caveat. The analysis showed that while RL dramatically increased the frequency of these behaviors, they were not positively correlated with higher accuracy at inference.
We've mistaken frequency for efficacy.
We have. The skill is unlocked, sure, but the model's actual performance ceiling is dictated by its latent knowledge, not by how often it tells itself to wait.
That is a fundamental challenge to the whole R10 narrative. Okay, let's shift to the optimization side, to the RL engine itself.
Yeah.
GRPO. It's popular because it's efficient, right? It estimates the advantage without needing a whole separate value model.
Right, but we need to break down the two critical biases they found in its objective function because they mechanically push the model towards really suboptimal behavior.
We'll start with the first one, the response level length bias. What's the mechanism?
It comes down to this one term in the objective,
Yeah.
1 over the length of the output. It's normalizing the policy loss. So think about it like this. For every correction signal, you're dividing it by how long the response was.
You're diluting the signal.
Exactly. And it creates this highly asymmetric learning environment.
So walk me through that. If the model gets an answer right, the advantage is positive. How does that dilution affect the update?
Well, for a correct answer, a shorter response gets a bigger, more impactful gradient update. And that's good. It favors being brief and efficient when you're right. The real problem is when the model is wrong.
So the advantage is negative, a penalty.
Right. And when that penalty is delivered, dividing it by a really long response length means the penalty gets significantly watered down.
Ah, I see it now. So if the model knows it's probably wrong, it learns that it can just write a massive wall of text to soften the blow.
Precisely. The longer the incorrect response, the less it feels the sting of failure. And this is what incentivizes the model to just keep writing, which everyone was mistakenly interpreting as this beneficial emergence of long chain of thought.
It's an artifact of the optimization, not a sign of deeper reasoning.
At least partially. It suggests the original R10 claims were, maybe misattributing a gradient artifact to genuine emergent behavior.
That's profound. Okay, so that's bias one. What's the second one? The question level difficulty bias.
That one comes from normalizing the reward by the standard deviation of returns across the group for a single question.
And what does that mean in practice?
It means you give higher weights during the update to questions where the standard deviation is low.
But a low standard deviation means what?
It means the question is either super easy, so all the generated answers were right, and the rewards are all near 1, or it's way too hard, and all the answers were wrong, so the rewards are all near 0.
So in either case, there's no variance.
Exactly. And GRPO then focuses its training effort on these questions, the ones the model either already aces or has no hope of solving.
So it's ignoring the most valuable training data, the questions where the model is right on the edge, where there's high variance and the most to learn.
It leads to a really non-uniform optimization. And what's fascinating is that the length bias isn't just a GRPO thing. The paper notes it's all over the place. Popular open source PPO libraries like Trollodol and OpenRLHF, they have the same issue.
A systemic problem, then.
It seems so. It's a misalignment with the theoretical PPO objective that seems to have crept into common practice.
So this is the core revelation. The tool was subtly broken. Now let's talk about the fix. Enter Dr. GRPO.
And Dr. GRPO is just beautiful in its simplicity. To get to unbiased optimization, you remove the two problem terms, you get rid of the length normalization, and you get rid of the standard deviation normalization.
So you're just recovering the standard PPO objective. The advantage is estimated by the Monte Carlo return with a simple, unbiased baseline, the mean return of the group.
No tricks, just clean optimization.
And the experimental validation.
It's very compelling. They ran GRPO and Dr. GRPO side by side on the Quen 2.5 model, and sure, both algorithms show length increasing with reward, but GRPO just keeps generating longer and longer responses, even when performance has totally plateaued.
While Dr. GRPO puts a stop to that.
It prevents the response lengths from spiraling out of control. It maintains efficiency.
And it's not just about total length, it's about the length of the incorrect answers, right?
Exactly. Dr. GRPO substantially reduces the length of wrong answers during evaluation. It confirms that it's mitigating that overthinking phenomenon. It stops the model from writing those long, rambling, incorrect chains that the biased penalty system was incentivizing.
And the ablation studies confirmed it was mostly the length bias causing this.
By far. The length bias was the much bigger driver of the length inflation compared to the difficulty bias.
And this focused, unbiased approach is what led to that incredible SOTA result. The OAT07B model, tuned with Dr. GRPO on Quen 2.5, Math 7B.
Hitting 43.3% on AIM 2024. It's just a testament to the power of getting the fundamentals of your optimization right.
It really confirms that RL scaling can work cleanly and efficiently if you can avoid the token bloat and the misattributed emergent behaviors.
Right.
So let's talk about some of the extended dynamics they observed, specifically this delicate dance between the template you use and the coverage of your training data.
Yes, and this section really reinforces that we have to be so careful about claiming pure RL gains. Remember how the Quen 2.5 base model was already strong at math?
Natively, without a template.
Well, when they applied any template to it, R1, Quen math didn't matter, it initially destroyed that base level math ability. RL then had to spend a ton of time just reconstructing a capability the model already had.
That is a huge efficiency cost. You're fighting the template before you even start reinforcing.
Yeah.
So how did the training data experiments play out with that in mind?
It was nuanced. In the large mismatch scenario, using the R1 template that really forced the Quen model into an unnatural structure.
It needed a lot of data to recover.
It needed a question set with really good coverage, like the ORZ57K set, to climb back to high performance. But in the small mismatch scenario,
Where the template was a better fit for the model.
the Quen math template, there, training on a much simpler, even out-of-distribution set like GSM-8K achieved the best final performance.
What does that tell you?
It suggests that RL's main job, when everything is aligned correctly, is to reinforce useful reasoning behaviors that are already latent. It's not about infusing brand new knowledge. It's a precision instrument, not a knowledge fire hose.
Reinforcement versus infusion. That's a
Yeah.
critical distinction. Okay, finally, the study looked at the ceiling effect of pre-training using a weaker model, Llama 3.23b.
Right, and they found that the vanilla llama model showed almost no RL gain. It just didn't have the base knowledge. But after they did continual pre-training on specialized math datasets,
Like fine math or Numina QA.
its RL performance ceiling shot way up. It just validates that embedding domain knowledge during pre-training is what raises the absolute maximum performance that RL can then later achieve.
And I'm assuming the GRPO bias showed up there too.
Oh, absolutely. Running GRPO on that pre-trained llama gave them that familiar double increase performance went up, but length went way up too. And again, Dr. GRPO mitigated the length increase while still capturing the performance gain. The fix works regardless of the base model.
So to wrap up our deep dive here, these sources really challenge the accepted wisdom about R10 training in three major ways.
They do. First, that base models, especially Quen 2.5, are far from pure. They have these critical pre-training biases. Second, that the aha moment isn't emergent. It's a latent behavior that RL just amplifies, and not always productively.
And most critically,
Most critically, that the GRPO algorithm itself contained quantifiable biases that were mechanically inflating response length. It was disguising token inefficiency as reasoning depth.
and the practical takeaway is that Dr. GRPO is a simple, essential fix. It maintains the reasoning gains while hugely enhancing token efficiency just by stopping the model from generating long, incorrect responses. It ensures that when we talk about emergent reasoning, we're actually talking about real progress, not just an optimization artifact.
Which leaves us with a final provocative thought for you to consider. We now know that the performance ceiling for RL is set by domain-specific pre-training. Yet we also see that the best RA results can sometimes come from training on simpler, out-of-domain questions as long as the template is right. So the question is, how should we prioritize? Should we focus on pre-training data purity or on the strategic design of a diverse, low-level RL curriculum to optimize these future reasoning models?
A fascinating dilemma for anyone building the next generation of these models. Thank you for guiding us through this essential work.